Hello, everybody. So, we finished talking about um, the Rutherford model for the atom and how, based on the scattering data that was collected by Rutherford's students, he was able to come up with a model for how the nucleus of an atom scatters alpha particles impingent upon it. The main conclusions, there was a bunch of interesting things that came out of the Rutherford model of the atom, but the most important conclusion that came from it was the idea that most of the mass of an atom is condensed in its nucleus, and the nucleus is composed of positively charged particles, right? So if the nucleus is dense and positively charged, a question that arises from this is, where does the rest of the nuclear mass come from? So remember Thomson's experiment, they were able to measure the mass to charge ratio for different things, and as the story goes, originally when looking at hydrogen, there was the expected peak for hydrogen with, associated with the mass to charge ratio for hydrogen. But then there were two other peaks, one that was heavier and another one that was heavier still, but both had the same charge. This was a question that wasn't originally answered by Thomson's work or Rutherford's work. Thomson's work led to the discovery of isotopes, but the explanation of isotopes and what they are would have to come later. If the nucleus is positively charged and dense, what keeps it from flying apart? This is the strong force. So the weak nuclear force is responsible for neutrons and the existence of neutrons, and also the changing from neutrons into protons and things of the sort, and, well, the decay process of the neutron, if you will. So this is associated with a weak nuclear force. What keeps the nucleus together is associated with the strong nuclear force. Both of these forces we're not going to talk about very much more in this class. We'll talk about the strong force a little bit later on when we talk about quantum mechanics, but to treat them in detail is beyond the scope of this course. Now the other question, though, is how do electrons move about the nucleus to form a stable atom, right? And how does this movement account for the observed absorption and emission spectra? So this is what we're going to spend the rest of this chapter talking about. Niels Bohr's model of the atom. So what do I mean by model of the atom and absorption and emission spectra? So this actually goes back to a time historically before we even knew about the existence of atoms at all. So this goes back even to the time of Isaac Newton, and just after Isaac Newton, approximately 100 years after Isaac Newton's work, people discovered atomic spectra. So initially, the first big idea came from when the white light, the black body radiation from our star, was split with a prism, and we see a continuous spectrum emerge from that. This is what we're familiar with in terms of the black body spectrum, right? We see that the prism breaks this light up into all these different wavelengths, a continuum of wavelengths, and we know from our study of black body radiation that this spectrum arises from the radiation being in thermal equilibrium at an associated temperature, right? But what's more interesting is if you look at the sun, right, as your black body, which is what originally occurred. If you look at the sun as a black body, in particular, a physicist by the name of Fraunhofer in Bavaria looked at spectral light through a prism and a telescope, and saw spectral light, solar light, light from our star, and saw that there were these black lines, these missing things inside this continuous spectrum, right? Things like this, and this, and this. So for some reason, there are wavelengths that just aren't there when we look at this continuous spectrum from the sun. And this is very, very confusing, and it wasn't understood, and Fraunhofer never actually was able to explain where these lines come from. A little bit later, Kirchhoff and Bunsen, and you engineering students know Kirchhoff, yes, that's the same Kirchhoff from KCl and KVL. And you chemists know Bunsen, that's the same Bunsen from Bunsen burner. And you cartoon fans know that's the same Bunsen from the Muppets, right? Bunsen honeydew. So what they did is, well, it's obviously not the Muppet, it's a scientist, but anyway. So if you look at a gas, so if we take some gas like hydrogen gas or helium gas or argon gas or sodium vapor or whatever, and we heat it up, it glows, right? When we look at the light from this glowing gas and we diffract it in a prism, we don't see a continuous spectrum like you might think that we would. So these hot dilute gases are clearly not black bodies. So the way that they are radiating is quite a bit different from the way that a black body emits electromagnetic radiation. In particular, they only emit at specific wavelengths, right? Which is what we see here. And the real connection came later on when people realized that the emission spectrum from certain atoms corresponded more or less with the absorption spectrum from solar radiation. So one famous person is Edward Charles Pickering, who looked at the light not just from our sun, but looked at the light from various stars and recorded the spectrum of the light from various stars in the sky. And there's all these really cool, I don't have any pictures of it in here, but there's these really cool old photographic plates that he had where you see like you would see like an image of the night sky with all the stars in them, but instead of individual stars, you see each one of those spread apart by a spectrum. So little spectral lines were all across the night sky. It's a really cool looking picture. But anyway, the work that came from this is this idea that, well, if light comes, if we have this continuous radiation that's coming out of the sun, but then the atmosphere of the sun is absorbing very specific wavelengths, that could correspond to the fact that, so say for example we have hydrogen. So if we have continuous white light coming out of the sun, and then we have hot hydrogen gas surrounding that in an atmosphere, that hot hydrogen gas could absorb these particular wavelengths and take them out of the spectrum, if you will. And so this was a really, really outstanding and stunning discovery when you think about it. So this was telling us that the things that stars are made of and the thing that, the Earth is made of, that planets are made of, is the same stuff. The atomic composition of the stars, the things that we can see in the universe, and the terrestrial objects that we can interact with here on our planet were the same thing. The universe is made of all the same stuff. And this kind of message, this secret message, so to speak, was hidden in the spectrum of light that we see from the light hitting our planet from the sun and from other stars every day. This secret was there. So from that, though, came, it was known and it was discovered that, well, we heat up these gases, we can see that they act like a fingerprint. So the emission spectrum of a gas works like a fingerprint of that gas. So if we can heat up some sample to the point where we heat it up and all the chemical bonds break and all that's left are its constituent elements in gaseous form, we can look at the spectrum of those and we can pick out what's there. In particular, what we can do is we can take a pure sample of an element, and we can compare the spectrum of some unknown sample to a pure sample of that element and see what elements are present. This is called atomic absorption. Sorry, guys. This is called atomic absorption spectroscopy. Now, the interesting thing about this is we can apply this same logic to the stars to figure out what's in the stars. But none of this really says anything about the existence of atoms, okay? None of this says anything. These are just fingerprints. It wasn't actually known definitively what these lines that you see correspond to. until along came Niels Bohr. But before that, what we have here is these lines. And so a lot of people at the time, and people after whom a lot of these things are named, in particular we have Balmer, who was actually a school teacher who came up with and discovered just by looking at these things, because this was known information, this was published, that hydrogen has this wavelength, this wavelength, this wavelength, this wavelength, this wavelength, right? And as more and more spectra were published, different characteristic wavelengths showed up. And various people were trying to see if there's some sort of special relationship between all of these things. Well, what was found was that there are different coefficients, and these wavelengths are actually related by these kind of simple little formula here, and there's a different coefficient for each of these, right? Now, what actually came from all of this is Balmer realized that all of these things are related by this simple little formula here. So 1 over the wavelength is equal to r, a constant, times 1 over one integer squared minus 1 over another integer squared, where this one and f is greater than ni, right? This thing we call the Rydberg constant. I can't remember if there's a D in there, I'm embarrassed to say. I can't remember if it's Rydberg or Rydberg, but whatever. So this number actually was able to unify, this pattern was able to unify all of these different things. So this was a really cool idea, and it was a school teacher that published this all on his own. So it was a really impressive thing. But what does this have to do with the structure of atoms? So, going back to the stuff we had already talked about, Rutherford and Thomson's experiments showed that atoms are mostly empty space with a dense positively charged nucleus and negative electrical charges floating around. Now, so think about this. If you have a positive charge in the nucleus and you have a negative charge in the electron, and that electron was sitting nearby at rest, what would happen? Well, we all know how Coulomb's law works. This is just going to get sucked right into here, and that's it. That's going to be the end of it. We know if we plot the potential energy as a function of distance, it goes right down to 0, ostensibly. So, we know that that couldn't happen. So, what has to happen instead came this idea of a planetary model of the atom. This is what people kind of thought after Rutherford and Thomson. So, Rutherford said that there has to be this dense nucleus rather than this old-fashioned kind of plum pudding model. So this dense nucleus, which means that these electrons can't just be sitting around it, they have to be moving, they have to be orbiting around it, or they'll get sucked in. But there's a problem with this. Unlike planets that are, we can have planets in the planetary model for the solar system, if we have a planet like the Earth, and we have, our star like the Sun, we can have the Earth orbiting around the Sun with a stable elliptical orbit, right? That elliptical orbit is characterized by 2 radii, right? That describe the size of this ellipse. Or if the 2 radii are the same, these 2 distances are the same, you would say it's just a radius. But this can all be very well predicted by Newton's law of universal gravitation. And so we know that each of these orbits, there's going to be a set of velocities, right, that correspond to orbits that will be stable, and the planet will continue to go around here unless some external force acts upon it. This orbit will be stable. And if the masses of these things were to change, the size of the orbit would change, because we know that Newton's law of universal gravitation right? We know how this works. So there's stable orbits. This can't work for electromagnetic radiation. It can't work. The reason is because, and if you guys didn't, if you think back to your Physics 2 class, you might have talked about something called Poynting's theorem. And I know we mentioned it very briefly earlier when we were talking about Hertz's experiment and electromagnetic radiation. But one of the consequences of Poynting's theorem is that when a charge is accelerated, it gives off electromagnetic radiation. We know, as a matter of fact, that that's one of the ways that charges can create electromagnetic radiation. If we take a charge and we wiggle it back and forth, we get radio waves. You guys know that's how oscillating circuits work. So the problem is that a charge that is accelerating will radiate. So think about what would happen here. If this charge, electron, was in this stable orbit around this nucleus, as it's accelerated, forced to move in this circular path, it's going to be radiating, right? As it does that, it loses energy. Therefore, the orbit gets smaller, right? And the orbit would get smaller and smaller and smaller until the same old thing that I talked about right here would happen. The electron would plummet into the nucleus, and there could be no stable atoms, the kind of atoms that Rutherford observed. Electrons outside and this dense nuclear radius, mostly empty space in between, that could not exist. So this was a huge problem in physics. How can an atom exist in this way if electrons behaved in the same way as, as we would expect them to according to our understanding of classical electrodynamics? This is a big problem. So guys, I'm not going to bring it up here, but I have a little Wolfram demonstration right here. If you guys download Wolfram Alpha or use your associated mathematical licenses that you get for being students here at our university, you can check this thing out and you can mess around with this kind of idea behind why point charges why charges radiate when they are accelerated, just to kind of line up your intuition for this. And this is actually also useful because this is relevant to our discussion of relativity from earlier in the course when we talked about how magnetic fields arise because we want to make electric fields Lorentz invariant. All right, but anyway, in comes Bohr, and he makes this very, very unheard of assumption. And this assumption was very powerful. I would almost say that Bohr's model of the atom and Bohr's idea is just as, if not more revolutionary than Max Planck's idea of energy quantization describing black body radiation. So what Bohr said, Bohr came up with his model of the atom, and this included 4 postulates. And the 4th one is by far the most important, but we'll get down to it. So first of all, the only force involved here is the Coulomb force. So protons and electrons, the nucleus and all the electrons circulating around the nucleus have to interact via the Coulomb force, right? Q1, Q2 over R squared. And we know in this case that K is equal to 1 over 4 pi epsilon 0. And in this case, Q1 times Q2 will be Z, which is the charge of the nucleus, times E squared. And we would have Z times a positive Z for the protons, then negative for the electron, right? Anyway, now this is the interesting 2 and 3, right? So 2 and 4. 3 you can almost think of as a consequence of 2 and 4. But he said that orbital radii have to be stationary states, and they do not radiate, right? So remember how we said as that charge gets closer and closer, as it plummets into the nucleus, it's giving off energy. So Bohr said, for some reason, we're just going to assume that that is not the case, that there have to be orbits or distances from the nucleus that behave like stationary states, right? And so if they are a stationary state, they would not radiate. They would represent a place where, as long as there's no external perturbation to the system, the electron would stay in that orbit forever. Nothing would knock it out of that orbit. Just like we can imagine that if planets will stay in the same orbit forever, just as long as there's nothing changing, changing their masses or changing the force between the planet and the thing and the star that it's orbiting, okay? Same idea here. So for a planetary model to work, if you will, certain radii have to be stationary states, right? So another thing about this, for these things to be stationary states, that implies that their angular momentum must be quantized, right? So each of these stationary states has to correspond to a quantized angular momentum. So you guys remember from Planck, right? He said that the energy associated with one of the oscillators giving rise to black body radiation had to be n times a constant times a frequency, right? So this n was our first example of what we call a quantum number, something that shows that a fundamental property of a system is quantized. So Bohr is now saying that we have this quantum number here, another n, pops up here, and that the angular momentum is quantized. So now what this means is that if the angular momentum is quantized, the energy will also be quantized, and I'm going to derive this for you on in the next slide. But the fact that the energy is quantized means that the energy associated with an atomic orbit, right, is going to be fixed. And what would have to happen is for a charge to radiate, for an atom to radiate, that implies jumping from one stationary state to another. And the frequency of light that comes out would be equal to the energy difference between those two stationary states. That implies that the spectrum that we see, these atomic emission spectrum, correspond to atoms emitting light as they go from an excited state down to a less excited state. So electrons jumping from one higher stationary state to another lower stationary state. Each of those states having their own quantized energy and their own quantized angular momentum. Okay, so let's work this out. But before I work this out and all the math that I'm going to show you guys, I'll go through this in more detail in a minute, but I just want to show you this picture. So the Bohr atom, the Bohr model for the atom was able to made the statement that all of these different things that we see, all of these different spectral lines are associated with electrons, like let's just say hydrogen, the Balmer series, electrons jumping from one state to another state, right? An electron that jumps from here to here has to give off this much energy associated with this jump, or this jump, or this jump, or this jump. So each of these things is going to give rise to a photon of a given wavelength, right? Or of a given frequency. So let's work through all of this. And what you'll see as we work through all of this is you'll see that what we get, sorry, let me get everything set up here. You'll see that what we get is something really exciting. We see that based on those four postulates that Bohr made, he was able to show that the Balmer formula arises from these four as a consequence of these four postulates. And he was able to predict the spectrum for for basically nearly all of the existing spectrum. There are more complicated things that were happening. Obviously, this isn't all there is to atomic physics, but he was able to come up with a physical model as a result of this that predicted all of these different transitions, right? So let's go through this so that we can see how this arises. So we have Bohr's model of the atom. So what did Bohr said? He had his four postulates. So one, protons and electrons interact via the Coulomb force. Next one, orbits. Certain orbits are stationary states. Radiation emitted corresponds to transitions between states so energy of the initial state minus the energy of the final state is going to be equal to h nu. And last but not least, angular momentum momentum of states is quantized. So we have L is equal to NH bar, where H bar is equal to H over 2 pi. Okay? All right, so let's go through all of this. So first, we're going to start with some simple things having to do with conservation of angular momentum and conservation of energy, right? So if we start out, we see that, let's see here. Okay, so we have our angular momentum. And of course, we know that the definition of angular momentum, we're talking about a stable orbit, right? So let me draw this up here, if there's room. So we will have our little nucleus, and we have our electron, and we have a radius, right? And we have a force. So this is going to be associated with, well, let me paraphrase. Let me draw these, use different colors here. Let's see, so I'll draw, we're going to have a velocity here, and we're going to have a Coulomb force pointing here. It's supposed to be in the same direction, right? So we know that these things are going to be 90 degrees to each other, okay? So going back down here, you can see that this is just going to mean that we have the radius times the mass of the electron times the velocity of the electron is going to be equal to an integer times h bar. So the magnitude of the angular momentum will be that. Now, what about our energy conservation? So let's start with energy conservation here. Let's come up with an expression for the total energy. So we know that the energy will be equal to the kinetic energy plus the potential energy, right? So no surprises here. 1/2 mass of the electron times its velocity squared, right? And we have here our potential energy. So we remember that the potential energy from Coulomb's law is just going to be K E squared. I'm assuming that the charge is 1 here, right, over R. So this is minus, of course, because we have a minus charge for the electron and a +1 for the proton. We're talking about hydrogen right now, okay? So +1 times -1 gives us a minus sign here, all right? Okay, so we can do some simplification here. Now, if we go back up here, and we can say this is in a stable orbit, so we have F equals ma. We're talking about a centripetal force, so we have the Coulomb force here, right? So we have K is equal to E squared over R squared. And this is going to be equal to the centripetal force, so this is the mass of the electron, times its velocity squared over R, right? With this here, we can see that we have something that we can put in for our kinetic energy. So if we divide both sides by 2, we see that we're going to be able to make some simple cancellations in our kinetic energy formula. Specifically, we're going to get that this is just equal to K E squared over 2R minus K E squared over R gives us minus K E squared over 2R. So now we have an expression for the total energy that just depends on the distance between the proton and the electron. So we don't have velocity in here at all. So now I'm going to change colors again and make another change. Well, another statement. I'm going to put the kinetic energy in terms of the angular momentum, and you guys will see in a minute why I'm doing this. Because the angular momentum is quantized, and if the angular momentum is quantized, we're going to be able to put our kinetic energy and then our total energy in terms of this same thing that's quantized. So we know that our kinetic energy is 1/2 MeV squared, right? We can write this as multiplying by 1, so if we have something over that same thing, that's just multiplying by 1. We can do that as much as we want. So we're going to take Me over Me, mass of the electron. We're going to do the same thing for R squared over R squared, right? Then we're just going to have MeV squared over 2, right? Nothing has changed except we know that L is equal to RMe times V. So if we move our terms around here, we can see that the kinetic energy is now going to be equal to, let's see, we have Me squared upstairs, V squared upstairs, R squared upstairs, so we have L squared over whatever is left downstairs, 2 Me times R squared. So now we have our kinetic energy in terms of our angular momentum. But remember, from above, we also know that our kinetic energy is equal to K. This is a lowercase k. This is, 1 over 4 pi epsilon 0 E squared over 2R. So once again, some stuff cancels out. That cancels out, that cancels out, that cancels out, that cancels out. And we can solve this equation for R, giving us our first important result. So this gives us that R is just equal to L squared over 2 times the mass of an electron times the charge of an electron squared times Coulomb's constant. Right? If we substitute in this Bohr's expression for the quantized angular momentum, we get, R is equal to n squared h bar squared over 2 mass of the electron, Coulomb's constant, electric charge squared, right? So what we can do is we can take all of these things out. We can see these are all constants, right? Except for one of them. Except for n. N is the only thing that changes. So we have n squared times what we'll say A0. And we want our little, there it is. Good. So this thing here is called the Bohr radius. And it has a value, if you look up all these fundamental constants, of about half an angstrom, 0.529 angstroms. Okay, cool. So what do we do next? Well, we take the other things that Bohr told us, and we can plug in get some other useful information out of this. So let's plug this back. Let me see how we're doing space-wise. Tons of space. Okay, so let's plug this back into our expression for the total energy. Right? Remember, we came up with an expression earlier of the total energy. The energy is going to be equal to minus k e squared over 2r, right? So let's figure out what the energy of something that's quantized would be. So if we put in our quantized radius, right, we get that the energy energy associated with a quantum number n is going to be equal to, we just substitute in what we just had for the Bohr radius in for r, and we get minus k e squared over 2 times A0 times 1 over n squared. And this is going to once again be equal to a constant over n squared minus 13.6 over n squared electron volts. And this is related to the Rydberg constant. And we'll see how it is so in a minute, which is another really cool thing that we see. We see now from this, we see energy of atomic orbits is quantized. So he said that they are stationary states, right? And by saying that their angular momentum is quantized, Bohr also, that implies, as you can see right here, that spacing or distance from nucleus is quantized. Yeah, this also deserves an exclamation point. It's a pretty big deal. Okay, so what else do we have? Well, let's take that last statement that Bohr made. Oh, excuse me, that Bohr made, not Born, not Max Born, Niels Bohr, two different guys. Okay, so the last one has to do with transitions between one state and another, one stationary state and another, one quantized radius and another. So let's say we make a transition, right, between an initial state and a final state. That transition is going to be associated with a photon of frequency nu, or a photon equivalently of wavelength lambda. Okay? So let's just put in our expression for the quantized energy. We have minus ke squared over 2a0 times 1 over ni squared. That was supposed to be a squared. Right? Minus a minus gives us plus ke squared over 2a0 times 1 over nf squared. Right? Now what we do, we move some constants around, and we see that we get 1 over lambda is going to be equal to ke squared over 2a0. Planck's constant comes down from the other side, and c also comes down from the other side, and we get 1 over nf squared minus 1 over ni squared. It turns out that this directly implies that 1 over lambda is r times 1 over nf squared minus 1 over ni squared. So Bohr's model was able to explain the Rydberg formula and all of this important stuff for the emission of radiation, or emission of light from stars, and the emission of light from atoms. So Bohr was able to say that what happens here, what we have here is, if we assume that in order for atoms to be stable, there have to be these stationary states where an electron can spin around a nucleus with quantized angular momentum. If that is true, that means that the distance from the nucleus is also quantized, and the energy associated with that is also quantized. From this, we're able to explain all of those absorption and emission spectra. So it's a really fundamental thing. It shows it was the next big step towards our understanding the structure of the atom, right? And we can see from this that it was able, as in addition to being able to reproduce all of this, another thing, we won't do this exercise, is you can imagine, well, what happens if our initial state was infinite, right? What do I mean by infinite? Well, let's just say that we had an electron that was infinitely far away, and then suddenly it was captured and came down into a final state of n equals 2 or n equals 1. this would predict the ionization energy of this atom, right? So in the case of hydrogen, you can predict the ionization energy of the hydrogen atom, turning it from a stable hydrogen atom into H plus an electron. That ionization energy was actually already known. And so because Bohr's data was able to recapitulate this, was able to show this, this was a really profound breakthrough and a very monumental discovery.